let me introduce Steve Zagarola. He is co-founder and managing partner of Northwest Center for Performance Excellence out in Portland, Oregon. So thanks, Steve, for joining us today. Steve's been designing studies and teaching with Stades' DOE software since his introduction to DOE from Douglas Montgomery in '92. He is an executive master black belt certified by the Six Sigma Management Institute. And he had provided technical editing for the 2012 edition of Six Sigma for Dummies by John Wiley. Steve has spent 24 years of his professional life working in engineering and management positions in diverse private industries, including high tech, energy generation, apparel, plastics, and food and beverage. And then 21 years as the founder and operator of 3 organizations dedicated to training, consulting, coaching, and mentoring individuals and organizations in things like Lean Six Sigma, statistical process control, design of experiments in both English and Spanish. And I just want to make an aside here that Steve will be giving our DOE crash course in December. So we're pleased to have him as a Spanish language person to give that DOE crash course for us. He founded Six Sigma programs at Portland State University, Oregon State University, and the University de San Francisco in Quito, Ecuador. So he has his mechanical engineering degree and postgraduate degrees in psychology from Georgia Tech and Georgia State University. So with that introduction, Steve, I'm turning it over to you. Thank you so much.
Okay, well, thank you, Sherry. You all can hear me fine, right?
Yep.
Okay, good. I'm going to go ahead and turn my ugly face off here a second, the camera, if I do that right. And you can still see my screen. And
perfect.
I'll put it in show mode. And you can still see it, right?
Yep, we're good to go.
Okay, fantastic. Well, thanks, Sherry, and thanks to Stades in general. I've been working with, as Sherry mentioned, I've been working with Stades for a long time. My initial learning, I was introduced to a very old version of Stades with Doug Montgomery a long time ago. Attended some of the classes up in Minneapolis, and enjoyed working with Stades people over the years. It's really been a boon to my own business, which I started back in 1990. I've worked on and off for employers and as an employer as well. So I've had various sundry businesses, all dedicated really to statistical quality, and more lately in the last several years to Lean Six Sigma. And this has always been my go-to software. So thanks again. So what I'm going to talk about today is really not centered so much on the DOE that we did, the case study, although it's going to be very central. It's going to really, the DOE case study is really going to be the vehicle for talking to you about how we teach or how we introduce design of experiments. And at the same time, and in the end, last few slides, we're going to talk about, which is really in a way the punchline, the idea that by running design experiments, particularly if that's way one is introduced in the early years when they get used to dealing with data, how valuable that actually is, because you start to realize in running and practicing, and particularly if you're teaching and learning DOE, you start to realize that those things that you learn in the practice of DOE are actually essential to understanding how to deal with any data. So for me, that's really the punchline, is that running DOEs, designing DOEs, teaching DOEs really is a great path to better understand how to deal with any data, how to look at data, how to critique data when people talk to you about data. And it kind of sneaks up on you, at least it did in my case. You may not realize in the beginning, but after you have the experience of dealing with DOE, you start to realize how really wonderful the methodology is and how valuable it actually is. That's really the gist. However, at the same time, I do want to share a case study. I can't reveal the client for which we did the work, and I have to be a little bit coy about how I talk about some of the things. So what I've really done here in the case study is given you an analogous situation with analogous factors. You'll see that as we go through. Okay, so let's go ahead and get started. So here's the topics: DOE, what and why. I used to work for, at one point in my career, I worked as a Six Sigma program manager for a company that builds wind turbines. Being in the energy industry, we often had to explain, no, DOE here is not Department of Energy. And so it's probably worthwhile to repeat that again, and that's usually where we start at DOE classes. What is DOE in the first place? Why would we do that? I'll present the case study very briefly. I'll give you a little bit of background. I'll talk about what I like to call the 5 cardinal rules of any good experimentation, which actually tells us a lot, again, about interpreting any data. We'll go through a 5-step protocol. You'll probably recognize that. You may not recognize it as a 5-step, but we kind of squeezed it. Being a Six Sigma professional, we kind of squeezed it into a DMAIC protocol. Those who are familiar with Six Sigma, you see how we did that. And then finally, what are the 12 lessons? Again, that's the punchline part. That's the part where we talk about what does this really say about data and how we look at data, how we critique other people's data, and how do we critique our own data. So DOE, what and why? DOE stands for not Department of Energy, but Design of Experiments. Well, also Department of Energy, but here the context is design of experiments or planned experimentation. It was actually one of the first ways I heard it articulated. It was actually very, very telling as well. What we found though, and let me go back here for a second. What we found though, or we find very often is if you talk to people about, well, what are you doing? We're doing a design experiment. Oh yeah, I did a design experiment the other day. What do you mean you did? Well, I changed that and I changed this. Nothing happened, so I tried something else. So we realized if you just take the term literally, that could have a lot of interpretations and it may not indeed be very effective. And so that was really the genesis of the so-called 5 cardinal rules that we're going to talk about. There are well-designed experiments and there are not so well-designed experiments. I looked up, I hadn't actually done that before. I looked up on the internet and saw how other people might define it. And here's, I think, a really pretty good one. This is from the National Institute of Standards and Technology. There's a lot of words there. I'm not going to read it to you, but what I'm going to do is kind of leave you with really what is the essence of a design experiment in the way that we like to talk about it. It's systematic. It applies principles and techniques that are supportable to support conclusions. And that key word there is support. Another key word, if you will, a constraint, right, on what we do is we do that with minimal expenditure. We'll see that also when we go through the 5 cardinal rules. For me, that's really the essence of what we mean. We as professionals applying DOE mean or should mean is in the way we should talk about it. It's not just any planned set of manipulating stuff, but rather systematic. It applies principles, techniques that support the conclusions, that we can defend the conclusions, and at minimal expenditure. So bravo to the National Institute of Standards. It's a great, actually, finding a really good resource in general for a lot of statistical stuff. So why do we do it? We do it to learn. You know, if we did nothing more than run experiment and just savor the knowledge we get out of it, I think it would still be worthwhile. As a child, I was always very curious, and to satisfy my curiosity, my mother bought me my first book on Guinness World Book of Records, so maybe this will answer all your questions. Well, now I found another vehicle, and that's DOE, just to learn, just for those of us who are curious. It guides us, right? Gives us information. That learning actually serves as a guide to how to manage and control our processes and optimize the process, and ultimately to optimize your processes. So DOE is not only to optimize, at least in my mind, it's about learning and leveraging that learning to do lots of things, to guide us, to optimize, just because we're curious, to invent, to innovate. It's a wide range of things we can do once we get that learning. For me, that's the real value in DOE. So here's our case study. As it says here in the subtext, based on a true story, creative liberties taken for a dramatic effect, because that's again, the case study isn't the main topic, it's just a vehicle and to make it somewhat entertaining, if you will, and to help you visualize what's going on, since I can't reveal the exact details of the names and so forth, we take a little bit of dramatic effect liberties in order to present that to you. Now, here's our case study. Imagine there's Acme, component design in manufacturing. I like the name Acme, I use that a lot because I'm a big fan of Coyote and Roadrunner, and so that name kind of sticks to me. I use that for a lot of my training and presentations. And then there's Pinnacle. There's a little joke in there, kind of, because Acme, if you look it up, you look at the definition, means kind of the top of, and so does Pinnacle. But Pinnacle, in this case, represents their customer. That is the customer of Acme, and Pinnacle actually does the assembly. So Acme is designing and manufacturing parts, and those parts, when they do that, have a number of choices, which we're going to see. Specifically, you'll see 8 that they decided to look at when they do that, but they then give those parts or sell those parts to Pinnacle, who does the final product assembly, as symbolized there in this little cartoon. Okay, part A, these are the parts that they supply, part A and part B, and then Pinnacle uses those parts to do assembly. So here's kind of what our assembly process looks like. Here's one case, they're perfectly aligned, right? They're gonna mesh together. That's a good assembly. So it's a non-defective, it's a good assembly, it's a good part. Here's one which is a little bit out of line, but still corrected itself, still a good assembly. So what that suggests, there is some leeway, there's a little bit of leeway. Here's another case, and in this case here, you can see not so good, right? So sometimes in the more off-center, the less aligned you might expect. Indeed, we're not always going to get a good assembly. The numbers you see there in parentheses, we'll talk about a little bit later, but basically those are going to be our factor levels in the design decisions for those parts. So the objective and the strategy of this whole study, and it's a series of studies, is the other thing that I wanted to take advantage of to talk to you about, is how, as Mark likes to talk to us a lot about. I've been to a lot of Mark's lectures and presentations, and talks about how we might start with say a lot of different factors, and we might narrow that down with some screening designs, and eventually optimize our process or our product, whatever it is that we're looking at. And so this is also an illustration of what we're actually doing here. So the overall objective and strategy here of these studies, these series of studies, design parts A and B, that's Acme, to minimize the vulnerability to defective assemblies during manufacturing. Pinnacle is the one, again, who does the final assembly in manufacturing. Okay. Yeah, here's the strategy. First, we're going to brainstorm. Nothing wrong with brainstorming. It's a great way to start. Once we do that, we're going to screen for some of those factors that we brainstormed. We're going to then follow up on what we learned in the screening. We're going to then optimize based on that follow-up. And then finally, we're going to control it. And we're going to talk about how DOE can actually help us with the control part. So that's our strategy. Okay, let's talk about brainstorming first. So here's our, being again, Six Sigma professional, we'd like to use fishbone diagrams. And so here's our fishbone diagram, and you can see at the head of the fish is defective assembly. That's the issue. That's the problem that we want to deal with. We're going to look at methods, materials, equipment, and measurement. So there's a factor A. Later I will reveal what A is. I will reveal what B is. And I can't reveal what D is. I can't reveal what G is, but G is material property. D was equipment property. The red ones that I'm showing now, these are controlled by Pinnacle. The blue ones are controlled by Acme. So there's variables also associated with the case study here that are under control by Pinnacle. So C is a method controlled by Pinnacle. E is also a method. F is a method or classified as a method, and H is measurement, the measurement that Pinnacle actually does. So we looked at those 8 factors. That was the initial study, 4 for Pinnacle and 4 for the equipment manufacturer Acme. Okay, now we're going to screen. I'm not going to go through the details here. It's a Plackett-Berman design. It's a little illustration of a Plackett-Berman fishing net, if you will. Put all those in there and filtered through, and lo and behold, what emerged were factors A, B, and C. And you can kind of see here by the size of these bubbles, the relative size of those as well. Indeed, C was the biggest one. C, now I've revealed, C is misalignment, and that's in the hands of Pinnacle. But A and B also have an effect, and those are the hands of Acme, the manufacturer. Okay, so that's our Plackett-Berman design. So the others go away. Now we're going to just focus on those that Acme control, A and B, that had a significant effect, and those that Pinnacle controls, which is controlled by Pinnacle, and also was a very big significant effect. Okay, next is follow-up. So that's our screening. Here we're going to get a little bit more detailed. We're actually not going to get a lot of details. It'll be a little bit further down after we talk about the 5 principles of the 5 cardinal rules that I alluded to earlier. Our follow-up, we did a 2-level design study. So we've only got 3 factors to deal with now because we've screened out everything else. We're going to look at 2-level design studies to screen further, if you will, screen for curvature and verify indeed that these factors do have some significant effects. So first, let's define. So part A is the blue part on the bottom, and the factor levels we're going to deal with are minus 0.13 millimeters up to plus 0.13 millimeters, and this is from the nominal. So you can consider these are deviation from the model. There's from the baseline or the nominal design, the original design. We're going to vary it by that much, a little bit less diameter, a little bit more diameter. Same thing on the top. This is part B. Here we're going to vary that when we do our DOE from minus 0.15 millimeters up to plus 0.15 millimeters from the current or from the original diameter for part B. For a misalignment, we're going to vary that. That can be anything, but we're going to vary that in our studies in a range that we think is actually typical, but not too extreme. And that is from 0, which is perfect, no misalignment, to up to 0.6 millimeters of misalignment. And again, that's in the control of Pinnacle, of the customer of Acme. So here's the 5 cardinal rules. Very quickly is differentiate. When we design an experiment, for it to be a good experiment, to be effective, to try to isolate effects, we first need to differentiate between noise and real effects. We need to identify interactions, right? We need to identify curvature if it exists, and we need to economize resources, as we talked about earlier. And ultimately, and if you think about the difference between a designed experiment and just observational data that existed for some reason over which we had no particular control, the reason that we do control in the case of a design experiment is to isolate cause and effect. That's really what we're trying to do, is to isolate cause and effect. So those are the 5 rules, but now we're going to illustrate those as we would if we were teaching this as an introductory course to DOE. So first rule, differentiate noise and real effects. We find a lot of people in our earliest classes aren't familiar with the concept of noise. They think you measure something, you do something, it gives you what it does without real consideration of variation. So this is actually a really, really important impact really on everything else that we actually do. Obviously, that's why statistics exist. So number 1, differentiate real noise and real effects. How can we do that? We can do that by running replicates. So let's do that. Let's run a few replicates. There's first one, second one, third, fourth one, fifth one. Let's see what kind of results we get. Let's go ahead and plot those. There's the first result, there's the second result, not the same, do the same 5 times, we're getting a little bit of difference. That's our noise. So the third result, it's the fourth result, fifth result, and if we continue with this over and over and over again, we might look something like this and actually might find a normal distribution emerging which represents what? Represents the noise, okay? If we instead just manipulated this between two levels, right, in order to understand if there's an effect, in this case, the effect of part B diameter, we will run it between the two levels we selected earlier, and it might look something like this. There's the first time we run the experiment, here's the second time we run the experiment, third time, and so forth. And in the end, we might get something that looks like this. So what's going on? Well, what can we conclude from this? It's really difficult, right? Because there's so much noise. Every time we do it, it looks a little bit different. We might even assume there is no effect at all, right? Or if there is, it's so minimal, it's not, quote, statistically significant. Now, in basic class, we may not understand what statistical significance is at this point, but we start introducing the terms. So we might just assume there's really no difference. This is just what? This is just a noise. Now, this is with misalignment at 0 millimeters, the perfect case, right? There's no misalignment. But let's see, what if instead we ran this again, one more trial, and we ran it again with some misalignment. We're going to go all the way to the edge of the range that we selected earlier. And now we see a completely different effect. So what's going on here? That's called an interaction. So we start now talking about interaction. So it's interesting to see that while it looks like part B diameter has no effect, as long as the alignment is fine, it does have pretty significant effect, practically significant effect, if indeed we go up to a higher amount of misalignment. If we go up to, in this case, the 0.6. So that allows us then to talk about interactions. So second cardinal rule is we need to identify if there are indeed interactions. And how can we do that? Well, we could run all combos and factors and levels. Let's try that. So we had two part B diameters, we have two misalignment levels, 4 combos, or written another way, we have 2 levels raised to second power, 2 factors, and that gives us a total of 4 combinations. So we have to run 4 combinations to be able to look at all levels and all factors for our little simple experiment at this point. So let's go ahead and do that. We have a secret code in DOE, which I always like to tell people. So you get a decoder ring right here before you leave class. And it looks something like this. Our low levels represented by secret code -1. And the actual levels for our 2 factors here are -0.15 millimeters and 0 millimeters for misalignment. Again, these are deviations. In both cases are actually deviations, but in the first case is deviation from the nominal. We have a code for high levels. And so here's high, we represent that with a +1, and a high level for part B diameter is 0.15 millimeters, and for misalignment is 0.6. This we talked about a little bit earlier. Okay, so let's go ahead and run this. There's our first experiment. If we only did, let me just go back a second. If we only did one factor, we could represent that with a line just like this. If we have 2 factors, then we might represent it like this. Construct what we call the design space. Okay, so we're giving a lot of new vocabulary to the students here. We probably would break at some point here and summarize what we've seen so far. There's a lot of new language, right, for our students. So let's go ahead and run that. Let's go ahead and run this out, finish designing that. There's our design, so-called design order or standard order, minus, plus, minus, plus for the first factor, minus, minus, plus, plus for the second factor. Now let's use our decoder rings and decode that. And that looks something like this, so -0.15 plus 0.15 and so forth, 0, 0, and plus 0.6 and plus 0.6. So there's our design. Okay, but let's replicate, right? We said before we needed to replicate, because if we don't replicate, how can we figure out what the noise is? How can we figure out what kind of natural variation that we actually get? What is the inherent variation in our process? We need to account for that. So we replicated. So we're going to do it again. Okay, let's go ahead and run the experiment. For those of you getting nervous that I haven't randomized, hold on, we're going to get to that a little bit later. But for now, let's go ahead and run the experiment like this. This is for the case that misalignment is 0.6. Remember, we replicated, so we have 2 results. This is when it was 0, and we have 2 results there as well. It's like a slight downward slope there, even with 0. Before we thought maybe it was flat, not quite sure because of all the noise, but looks like it again here. So let's see what happens. Let's just take kind of the average of those, right? And it looks like that. I'm going to draw this, how we think things are working at this point. This is how we think things might be working. Okay, so let's flip that around. Sometimes it's helpful. Let's go back a second. That's how we looked at it first. Notice here, misalignment, we had 2 levels of misalignment, but we're looking in effect, looking at the effect of part B diameter. Here we're just flipping that around, right? We're taking part B diameter and now showing 2 levels of part B diameter, 2 cases, 2 levels of part B diameter, and we're looking at the effect of misalignment. It's helpful, right? Helpful to look at it with 2 different perspectives. Okay, third rule, identify curvature. So we drew a line like this, but what gave us the right to do that? So I'm going to draw instead of a solid line, I'm going to draw a dotted line to suggest that it's tentative. What can we do about that? How can we test it? Well, we can run what are known as center points, obviously in the center. So in the center here, in this 1 factor experiment is 0.3. So let's run 0.3, and if it came out right there, then we feel, oh, maybe you can make that line solid. But if instead it looked like that, then it may be the actual case looks something like this. And this is exactly why we put in a center point, to detect this possibility. Now, it's pretty simple with 1 factor. What if we have 2 factors? What would that look like? Well, same thing. Still going to do something in the center, but now it's in the center for both of those factors. Okay, so there's our design space, the 2-level factorial with a center point right smack in the center, as the name suggests. Okay, so now let's go ahead and expand this, put in our center points. Remember, we're replicating, at this point, we're replicating everything. It looks kind of like that. Okay, let's go ahead and run the experiment, see what happens. Well, there's our 2 factors, draw solid lines, but you know, they really should be dotted lines. And if it turns out that the center point actually gives a result not in the center, and indeed up here at the top, then it looks like those dotted lines probably are not really indicative of what's actually going on. But we don't know, as unlike in the 1 factor design, we don't know which one of these are curved. So we have to do a little bit more work, and we might do something like this. We might add something called axial points, right? We might do that. And then we could start to look at the possibility of actually modeling the curvature, figure out which one indeed is the one that is causing that curvature, or both of them. We don't know yet. And we might do something like that. But before I do that, I need to consider the next rule, and that is economize resources. So here's an idea. We can start with 2-level design, screen for curvature with a center point, replicate on the center points, design fractionals, design multiple small experiments instead of 1. These are all kind of strategies I might have available to me. So let's do that. Here is if we did that monstrous experiment, we'd have 243 combinations, right? If instead I did a 2-level, down that's down to 32. I still want my center point in there, so I could put a center point in there to detect curvature. Okay, maybe I could just replicate on the center point instead of all those factorial points, all those points there in the corners. That would reduce it down to 36. That would be pretty good. Then maybe I could use fractionals, right? Maybe I violate one of the rules I talked about earlier and not look at all combinations, selectively pull some of those out just for screening, right? I could do that. Now I'm down to 20 runs. But if I have 10 factors and apply the same strategy, then I'm back up to 516 runs. But what I could do instead is I could, instead of running 10 all at once, maybe I could run 5 and 5, and I could do fractionals of those. And now we're down to 40. Okay, so these are the strategies, and the point of these last series of slides is to illustrate different strategies that we can use that are available to us in order to economize, in order to reduce the number of resources we need to expend in actually realizing this experiment. Okay, next, isolate cause and effect. Here's an idea. How about if we randomize order? Sometimes we might block, we need to document. So this is the standard order. Let's go ahead and, let's see, before we do that, let's look, geez, what if I can only run these first 4 in the morning, and I have to take a lunch break, of course, and then I come back and I have to run these in the afternoon. What if that is the effect? So to avoid that, one thing I could do is randomize the run order, or I could block. Now it's going to be a little bigger if I'm blocking, but first thing I would do is assign the blocks and replicate. I would then segregate those blocks like this into the blocks indeed, and then I would randomize within those blocks. So that's another option I have if indeed it's totally unavoidable and there's really significant risk that there could be some block effect, that is some effect from morning to afternoon or batch to batch. Okay. Next, we want to document held constant variables, conditions that could affect the results in the unusual event. Just at this point, you're a scientist, and we need to document everything that's actually going on as we run this experiment. So there's the 5 cardinal rules. Won't read them to you again, but this is kind of our summary. Differentiate noise and real effects, identify interactions, identify curvature, economize resources, and isolate cause and effect. All this needs a protocol. How do we do this? What are the steps? So here's a protocol with the example that we talked before, the case study we talked about before. I'm going to squeeze these into a protocol that's using Six Sigma, which is define, measure, analyze, improve, and control. And you can see how nicely it actually, protocols we might be used to and do actually fit into that articulation, if you will. Okay, so define, we're going to define the objective, name the response variables, name control factors and levels, define document held constant variables, name nuisance variables and strategies, and design studies. So let's do that. Design parts A and B, ACME, to design to minimize vulnerability to defective assemblies during manufacturing, we saw already, right? Name the response variables. Here's a good assembly and defective assembly. Name the control factors and levels we talked about earlier. Define document held constant variables. Maybe it's assembly speed, maybe it's assembly stroke, maybe it's feed material, maybe there's other things that we need to hold. In fact, we looked at a lot of different factors in the beginning and screened those out, but maybe it'd be good to hold those constant for now. Name nuisance variables, things that might affect our results that are kind of difficult to control, right? And then finally, run in random order, wait 15 minutes after feedstock change, wait 5 minutes after line stop, document ambient temperature, raw material, relative humidity, raw materials, lot numbers, validate measurement process, okay? Then we're gonna go ahead and design a study. 3-factor, 2-level factorial designs, 4 center points. Looks something like this, okay? Go ahead and randomize that. That's randomized. And now we're going to measure. Here's our measurements. So in measure, we need to define the methods, confirm the calibration, confirm gauge repeatability, reproducibility, and run the DOE and measure the responses. So here again, the factors, and here's how we're measuring it. Here's, we talk about calibration. We're going to check calibration. We're going to run our R&R studies, reproducibility, repeatability, and then we're going to run the study. And here are the results from our study. Okay, now we're going to analyze that. We're going to select statistically significant effects, model, plot the effects. Okay, so there's the results. There's our half normal curve in which we can detect the significant effects. Right, all p-values here for those selected are less than 0.05. The curvature also, okay, so that means we have some curvature. And the lack of fit is not, and that's fantastic. There's one effect we don't want to be significant. We've done a pretty good job of explaining most of the noise, what that model looks like. And here, then we get a model. This is always the fun part. Once we get a model, we can do a bunch of stuff with that. Let's look at what this looks like visually. Here's the AC interaction, right? Shown one way, and now kind of, oh, these center points, remember they were very significant. Indeed, now we can see why. Let's flip this around, let's look at it a different way. Two ways to look at the same thing, right? Here, misalignment, to have two levels of misalignment. We're looking at defective part A versus here we're looking at defective misalignment for two levels of part A. Here's the BC interaction. Center points are still there as they should be. And that's one way, looking at misalignment effect for two conditions of part B diameter. And then we can flip that around and look at it this way. It helps to look at it both different ways. A little bit different senses to what's actually going on. Now we're going to improve. Okay. Now in this improvement, a little bit complex versus some, because we can't just go ahead and optimize this because really we haven't met all the objectives. We want to make it non-vulnerable, insensitive to defect to alignment in terms of creating defective assemblies, number one. Number two, we had curvature. So to really understand this, we actually need to do one more set of experiments, okay? So again, the way to think of this is maximize robustness. We're going to focus on robustness here as we get toward the end of this last DOE that we're going to illustrate. Design for curvilinearity, difficult to pronounce. See if there's any curves in there in the model. We're going to measure, analyze the model. We're going to minimize percent defective, then we're going to predict and confirm the minimum percent defective. Then we're going to maximize robustness and visualize that improvement. So once we went ahead and designed the last series of studies, we just did that by taking advantage of what we'd already done, right? Augmented that to an optimal design. It looks something like the illustration up there. These are the factors, same factors, of course. These are the responses, same responses. Okay, and here's our study with the results. Here are the analysis. You can see the high significance of all factors, A, B, C, A, B, A, C, B, C, A squared, C squared. So there's our curvature. Note this was after a log transformation. And you can see our fit statistics looks like we're fitting pretty darn good. So we like that. And just another look here. Again, you can see this is after the log transformation. That's why you see the box Cox like it is there. This is after the transformation. Okay. And let's look at our interaction plots. Look pretty fancy. So that's always impressive to new students. Those nice little curves there. Now let's go ahead and optimize. Well, first part of optimization, we're going to minimize defective assemblies. So we set our little ramps in Design Expert where we'd like them to be. We'd like no defective assemblies, obviously, right? That's the desired result. This is what it looks like before and what we actually observed for the original settings. And this is after we did what Design Expert suggested that we might do in order to minimize the defectives. Okay, and you can see the relative results. See how we reduce the number of defective assemblies. Here's our confirmation. This is our prediction, and this is our actual result. Okay. Now let's look at the other component of this, and that's the robustness. This is what it's looked like before for the original settings. Look at the red line for misalignment and look how steep that is as you move away from zero misalignment. Interesting that it curves back down. I'm not quite sure why that would be, but anyway, this is what we saw. Look at it afterwards and look how that kind of flattens out. So what that suggests is that now as misalignment occurs, we're really not having a huge effect on our ability to reduce minimum defects. So another way, kind of a cute way to look at the robustness and at the same time look at the optimum settings. So if we start here, this is with, if you look to the left, you'll see on the left side of the screen, you'll see perfect alignment, no alignment. We would expect pretty close, not exactly, but pretty close to 0 defects. But we're going to start misaligning and see what happens here in this kind of animation. 1/10 of a millimeter, 2/10 of a millimeter, 3/10 of a millimeter, 4/10 of a millimeter, 5/10, and then 6/10. This is where it, again, for some reason, drops down a little bit. But you can see how robust it is. So we have a lot of nice flat area there before we start getting in trouble, and that's what you want. So we're getting results much better than we had before with the nominal dimensions of our part B and part A diameters. And we have some flexibility actually to maintain fairly low that flat part of the curve, okay? Now controls. So how do we use Design Expert to help us control? How do we use design experiments to help us control? Well, we can define targets, define process windows. If we go for what used to be very popular AQL level, 0.65%, then it's wide open, right? If we set up to optimum settings, then we can pretty much design anywhere we want. We have a lot of flexibility of our diameter. If we have no misalignment, we can run anywhere we want with the diameter A and B. If we get a little bit of misalignment, here's at 0.10 millimeters, then our windows start to separate out like this. A little bit more misalignment looks like this, and finally a little more alignment now is starting to disappear. So we're kind of getting an idea from this how far we can actually go, what we should tell also our client, our customer, Pinnacle, what they need to be aware of and what their tolerance is for any misalignment. And this is suggesting to us, we don't really, if we don't want more than 0.65% defective, then their limit should be probably no more than about 20.20 millimeters. So summary, here's our protocol. DMAIC, Six Sigma, DOE, define objective, name response variables, name control factors, levels, define document, held, constant variables, name distance variables, strategies, design the study, measure, define the methods, confirm calibration, confirm gauge R&R, run combos, measure responses, analyze, select statistically significant effects, model, diagnose, optimize, model, plot effects, improve, define improvement criteria, develop solutions, predict improvement, confirm predictions, visualize improvements, examine robustness, and finally control, define the targets in the process window. So that's the case study. That's fundamentally how we go about teaching the introduction to DOE. Not in 45 minutes, we do have a longer period of time, obviously. But as I said, the punchline here for me is lessons for deriving meaning from any data. We learn a lot from the DOE, and sometimes we don't probably even realize that. I actually teach now also an introduction to quantitative methods at Portland State University, and so this DOE background has really come in handy in speaking to that one. And that one we're talking primarily about observational data. So lesson one, define your range of interest, whether you're doing this to characterize something, whether you're doing this to discover cause and effect, whether you're doing this to quantify cause and effect, whether you're doing your study to predict or to optimize or compare and select. Define. Lesson number one, any kind of data. Validate your measurement system, any kind of data. Calibration, gauge R&R. How do you measure? Is it relevant? Distinguish noise versus effects, any kind of data, right? Not valid if we haven't done that. Isolate those effects. Is it day 1, day 2, day 3 that caused the effect here, or is it the relative humidity changing from 90% to 70% to 50%? Right? Isolate the effects. This is an example from a different study in which we were actually changing supposedly pressure. The way we did this was actually by turns on this lock screw. So really the factor was the turns. We don't know what the pressure was. In fact, we don't even know if it affected pressure, even if that was the intent. So it's really important to be careful about what you define as what is the real effect that you've been able to discover, okay? So distinguish between actual factors any assumed factors for any data. Lesson 6, consider effects conditional. Both things in life, it turns out to be, are conditional. They're not absolute. Science has showed us that over and over again. In interactions, is just a microcosm, if you will, of that same idea. Okay. 7, view relationships from multiple perspectives. It helps the brain, it helps people understand. Some people see it differently. So looking at it different ways is very useful in looking at data. Test linearity, right? Confirm predictions. Cautious with extrapolation. We don't know what happens beyond this design space, right? And combine data and visuals to communicate results. Very important that we communicate in ways that people understand, and that we can do that quickly. And the combination of data and visuals is very useful in doing that. And finally, most importantly, open your mind. So often we'll go into these and we actually go to run for our clients, run design experiments or help them do that, is they all have preconceptions as to what it should be. And one of the things we need to keep reminding them, this may look a little different than what you're used to, because maybe we really never looked at it this way before. Once they've done this a few times and see interactions and see all the surprises that often come out of these studies, then that's an easy argument. But in the beginning, sometimes it's difficult. So really important is to open your mind. That's what I have for you. Thank you. Happy experimenting. And I guess we'll open it now for questions. Thank you.
Great. Thank you so much, Steve. We appreciate that. Mike, who I know teaches DOE at his own organization, says that he says a very common complaint we encounter around DOEs are somebody saying, it didn't tell me anything, or I didn't learn anything.
Yeah.
My counter is there is learning, it just might not align with conscious or subconscious pre-experiment bias of the outcome. It's up to the experimenter to be open to the learning. You said that. How do you how often do you encounter that complaint? Maybe how do you respond?
Yeah, so I'll put my, since I'm answering people now, I'm going to put my camera on. Oh, absolutely. I tell people, you did learn something. You learned that you don't have any effect, or you don't have any significant effect. And we have to remind them, we don't know that there's no effect, right? We just know that the effect wasn't strong enough given the amount of inherent variation or noise that exists, that we're able to see it. Now, if you're sure there's an effect, then we can open up the range a little bit. Maybe we can, in effect, turn up the amplifier on the signal. If there's one there, we could do that. But just the fact that we learn something, or we conclude ultimately there is no effect, that in itself is learning, and that can be very valuable learning. So there's no way out of learning, even if you get no effect. We get the question all the time. Absolutely.
Yes, I agree. And yeah, we hear that at studies also. And I remind people that it is as important to discover which things do not have a significant effect on their process as it is to find the things that are significant in the process.
Absolutely.
It might be something, you might be looking for robustness. In fact, there's an entire DOE category that's about robustness or ruggedness testing, validation testing.
Absolutely. A lot of times we'll tell them, we didn't find effect. That's good news. You don't have to worry. We can change these things within these ranges, no problem, and then you don't have to worry. So that absolutely could be the best result that you would like.
I'm not seeing anything else. So Steve, I want to thank you. It was a great summary. I love seeing how somebody else summarizes, the whole process of a good DOE. You touched on everything in that, about 45 minutes of timing. So great. And I look forward to hearing from you again in the future.